Greetings to everyone, and welcome to session 5 of the IPPW webinar series on the topic today of surface sample return from asteroids and Mars. My name is Ashley Corzin from NASA's Langley Research Center, and I'm the U.S. Chair of the International Organizing Committee for IPPW. For today's webinar, we're delighted to be joined by our colleagues in Japan, Australia, South Korea, and many other places around the world during what are hopefully more sunlit hours of the day for this session in our webinar series. For those of you who are new to this community, the International Planetary Probe Workshop, or IPPW, is an annual congregation of scientists, engineers, and technologists from around the world working in disciplines supporting the development and flight of planetary probes for exploration. The first IPPW was held in Lisbon, Portugal in 2003. And in the years since, IPPW has alternated between the US and Europe as a nearly annual event. So while we were unfortunately unable to hold this year's workshop as an in-person event, it's truly great to see so many familiar and also new names joining us for this virtual webinar series. All this said, we're extremely excited to be holding IPPW 2021 next September in Tokyo, Japan. This will be the first time that IPPW will be held outside of the US and Europe. An introduction to IPPW 2021 will be given by the local organizing committee following the presentations today, so please stick around if you're able to for the duration of this session. Today's session is focused on sample return, with the first talk on the Hayabusa 2 mission, followed by a talk on Mars sample return and the Earth entry vehicle. With that, welcome to everyone online, and I'd like to turn it over to my co-convener for this session. So, Marcus?
Thank you, Ashley. So, first off, I'd like to introduce Dr. Hitoshi Kuninaka from JAXA, who will be giving our first talk. So, Dr. Kuninaka received his PhD from the University of Tokyo in 1988. At JAXA, he was promoted to associate professor in 2000 and to professor in 2005. Concurrently, he held the post of professor in the Department of Aeronautics and Astronautics at the University of Tokyo from 2004 to 2018. And 2 years ago, he became the Director General of the JAXA Institute of Space and Astronautical Science, or ISIS as it's known, as well as Vice President at JAXA. Dr. Kuninaka researches the plasma interaction of satellites as well as leading development of electric propulsion systems. He participated in the satellite project Space Flyer Unit from 1988 to 1996. Which was successfully brought back to Earth via the Space Shuttle mission STS-72. Microwave discharge ion engines, which were invented and developed by Dr. Kuninaka, took the first Hayabusa spacecraft on the round-trip journey between Earth and asteroid Itokawa from 2003 to 2010. Ion engines have been propelling the Hayabusa 2 Explorer in its mission to asteroid Ryugu since 2014, and Dr. Kuninaka will be talking much more about this shortly. The Hayabusa project team has been honored with several awards, including the NSS Space Pioneer Award, the AIAA Electric Propulsion Outstanding Technical Achievement Award, NSS Von Braun Award, IAA Laurels for Team Achievement, among others. Dr. Kuninaka became an AIAA Fellow in 2012 and IAA Space Engineering Section member in 2019. So without further ado, let me turn over to Dr. Kuninaka to talk to you more about Hayabusa 2 and JAXA's efforts in planetary exploration.
Okay, thank you very much, Marcus. So, good morning, everyone. So, Japanese local time is June 26, 8 a.m. So, I would like to present you our activity, and then I can show you my presentation material. So, can you see my presentation material? How about Marcus? It is okay?
Yes, we can see it. Thank you.
Okay, thank you very much. So title is the JAXA Planetary Exploration Programs. So in this presentation, I would like to focus on the project of the Hayabusa 2 asteroid sample return mission. And then, first page show you original Hayabusa 1 spacecraft brought back the material of the asteroid Itokawa while establishing the innovative ion engine. And then based on the achievement of Hayabusa 1, we are now executing the Hayabusa 2 mission, similar mission, asteroid sample return from the asteroid Ryugu. And then so you can see Hayabusa has already finished, but that is about 500 kilogram, very tiny spacecraft. And then Hayabusa 1 explore the Itokawa asteroid, and it was launched 2003, and it came back to Earth 2010, 10 years ago. And then, so we are now executing the Hayabusa 2, that is almost same as weight mass, about 600 kilogram. And then, so it explored asteroid Ryugu. It was launched 2014, and last year, 2018, we investigate asteroid Ryugu, and now on the way to Earth, and it will come back as end of this year, December 2020, this year. And then, so this page shows you the mission outline, sequence of events of Hayabusa 2. It was launched December 2014, and then so it executed the maneuver from the Earth and the asteroid, and then executed the rendezvous with asteroid Ryugu, June 2018. And then we executed the several operations around the asteroid. So some of them is the very exciting experiment, that is to make artificial crater on the surface of the asteroid using the impactor, and last year. And then we try to execute the touchdown operation vicinity of the artificial crater in order to collect the new sample, asteroid sample. And now spacecraft on the way to Earth. And at the end of this year, spacecraft will come back to Earth. And as at the moment, surface SRC sample retrieval capsule will drop on the surface of, will drop to Earth. And then, so I have already explained you, Hayabusa and Hayabusa 2 is a very tiny spacecraft, around 500 kilogram, but they have the capability to explore long range. It is because of the ion engine. So ion engine exhausts very high velocity, 30 kilometers per second, very high speed. In that sense, the propellant utilization efficiency is very good, so 10 times efficient in comparison of the chemical propulsion system. And then in the world, we have several types of the ion engine, Kaufman ion engine, and the Ring-clasp ion engine, and RF ion engine. But the JAXA, ITAS succeeded to develop the new types of the ion engine, microwave discharge one. And then so Hayabusa and Hayabusa 2 install the microwave discharge type ion engine, and then they have a long range capability to explore solar system. And then so I would like to focus on the operation of Hayabusa 2. This page shows you the orbit of the Hayabusa 2. So Hayabusa was input the vicinity of the Earth orbit. So it means the Earth 1 year Earth synchronous orbit, and then so 1 year later it executed the Earth by, and the spacecraft was input to the large eclipse orbit, and then to circulation around the sun. Spacecraft succeeded to the rendezvous with asteroid Ryugu, July 2018. But on this maneuver, ion engine takes a very important role, and for the as the main propulsion system of the Hayabusa 1 and 2. And then, so this page shows you the figure of the asteroid Itokawa and asteroid Ryugu. Asteroid Itokawa was explored by Hayabusa 1. That is a very tiny object. So tip-to-tip length is about 600 meter. S-type asteroid. S means stone-type asteroid. On the other hand, asteroid Ryugu is a C-type asteroid, spin top shape. Diameter is about 1 kilometer, a relatively large asteroid. And then, this page shows you the explanation of the artificial crater formation operation. So spacecraft installs the impactor, and then spacecraft release the impactor, and then so after that the impactor automatically ignites after the 40 minutes later after the separation, and then such time duration Hayabusa 2 takes the escape maneuver in order to avoid from the collision of the a lot of the fragments. And then so spacecraft take the will go to the another side of the asteroid. But on the way to the escape maneuver, spacecraft drop the deployment camera in order to observe the phenomena of the impact moment. And then this page is this is a computer graphic for the to explain the escape maneuver. Now spacecraft go to the another side of the asteroid, and on the way to escape, spacecraft drop the deployment camera in order to observe the impact phenomena. So now new crater is formated. So in order to realize this phenomena, we developed the impactor. So this movie shows the exact operation, full-scale demonstration test on the ground. Impactor is located here and then accelerated this way. So once gunpowder ignites, and then so accelerate 2 kilogram pallet, and then accelerated to the 2 kilometer per second, and then you can see 2 screens were penetrated by the impactor, and then so and then 100 meters downrange, so we have a sound target impactor right on the sound target. So this is the full-scale demonstration on the ground. So it was operated in the vicinity of the asteroid Ryugu. So this is the image of the exact observation by DCAM camera. You can see a lot of the ejector was emanated from the artificial crater. So this data is very important to investigate the physics of the asteroid surface. So so DCAM observes the phenomena of the impactor operation, such kind of just like it. And then so vicinity of the artificial crater, a lot of the fragment is emanated, and then but these tiny material were swept by the solar radiation or asteroid gravitational field, and then whole of the materials swept and vanished, and then 1 month later, spacecraft come back to the impact location, and we observe the new crater. And then so this page shows you the comparison of the after and before impact location. And then so we identify the artificial crater. The diameter is about 15 meters. And then so we executed the touchdown operation vicinity of the new crater. This is the exact telemetry data at the moment of the touchdown operation. So white nozzle is the material sample capture mechanisms, and then so at that moment of the touchdown operation, we collect the material of the asteroid. And then now on the way to Earth, and then we would like to execute the SRC retrieval operation. So this page shows you the operation sequence of the Hayabusa original. So on the way to the Earth, ion engine takes the main propulsion system to go back from the asteroid Itokawa to Earth, and then after finish of the delta V maneuver of the ion engine, we take the TCM. TCM means the trajectory correction maneuver. TCM 0, TCM 1, TCM 2, and then at the moment of TCM 3, we change the target from Earth rim to Australia Umera. And then TCM 4, we precise guide to the landing point of the Umera of the Australia. This is a sequence of the guidance sequence of the SRC to WPA Umera prohibited area. So this page explains the another feature of the guidance sequence. So this is the B plane. So imaginary crossing point on the B plane, and then so on the B plane guidance sequence, TCM 0 or imaginary crossing point is gradually approaching to the Earth, and then so disk of the 16,000 kilometer disk on the B plane, it is equal to the collision to the Earth. And the TCM3, we change it to the imaginary crossing point inside 16,000 kilometer disk inside. So TCM3 means the landing point, landing dispersion eclipse on the Umera area. So Umera is a very large area. North, east, and the west range is 500 kilometers, but the landing dispersion eclipse is very large. And then so this is a TCM3, and after that we executed the TCM4, and then we targeted the much precise landing area about 30 kilometers. So and then after that we executed the SRC drop sequence. So our Hayabusa and Hayabusa 2 sample return capsule is a very tiny one. Diameter is about 40 centimeters. Total weight is 16 kilograms. And then so, but the very smart and the versatile system. It includes the parachute and the beacon system, and the automatic operational sequence is executed by automatically. And then so this is the exact re-entry operation at the moment of the Hayabusa 1 SRC. It was executed June 13, 2010, 10 years ago. So now at this moment, we executed the whole of spacecraft was enter the atmosphere. So now spacecraft dive to the atmosphere 12 kilometers per second, and then whole of the spacecraft has decayed in the Earth atmosphere. And then so spacecraft completely destroyed in the Earth, but the so you can see the stable flight system, that is the re-entry vehicle. And then after that, spacecraft deployed the parachute and then executed the soft landing on the surface of the Earth in the Umera area. And then so 1 hour later, on the landing on the capsule, we identify the safety landing on the capsule by herringbone observation. And then after the daybreak, we went to the landing point, and then we are now observing the reentry vehicle. So these are the parachute. This is me. In those days, I was the capsule retrieval team leader, and several days later, we transported the capsule system from Umera to Japan directly by charter flight. These are the sequence of the Hayabusa 1 capsule retrieval operation. And then so now we are executing the Hayabusa 2 comeback mission. And at the end of this year, we will retry the capsule retrieval operation at the Australia, Umera, again. And then so in the parallel to the Hayabusa 1 and 2, we are now executing the lot of the exploration program in the solar system. This page shows you the Bepi Colombo mission. So this is the joint mission with ESA and the JAXA. We are now sending the Bepi Colombo NEO, our spacecraft, to Mercury. It will be arrived at the Mercury in 2025. And the Akatsuki, this is a Venus probe. It is now circulating around the Venus to observe the climate observation of the Venus. And we are now developing the SLIM. SLIM means Smart Lander for Investigating Moon. It will be launched in 2022 for the precise landing on the surface of the moon. And MMX, Martian Moon Exploration. We are now developing the MMX for aiming for sample return from Phobos, Martian Moon. So, so this page shows you the JAXA's strategy to apply small probes in deep space. So MMX is a relatively large spacecraft, about 4 tons at the launch mass, but the Hayabusa 2 rated around the 500 kilogram, very tiny spacecraft. But using the ion engine technology, we realize the long-range capability such like that, like Hayabusa and Hayabusa 2, and the SRC and the around 16 kilogram. SCI is the impactor is only 10 kilogram. So integrating the small probes, we would like to explore solar system. And then another feature of the ISA small body exploration strategy, we are focused on the small body because the small body takes an important role. So material transportation inside solar system. So water on ice and evaporating material on organic material was transported from the icy Jupiter on Saturn outside of the solar system. This material was transported from the inside rocky planet. And then so we believe the asteroid and comet played very important role for material transportation inside solar system. And then so in order to investigate in such physics, we would like to execute the periodical sample return. Hayabusa executed the sample return from the asteroid Itokawa 2010. And then 10 years later, this year, Hayabusa 2 will take the sample return from the asteroid Ryugu. And then 2029, MMX will bring the sample from the Phobos. And then so this kind of the periodical sample return is the JAXA's strategy to explore solar system. And then integrating the whole of the spacecraft, such kind, relatively tiny spacecraft, we explore solar system that bypass deep space filter. Oh, thank you very much. That is the all of my presentation material.
Thank you, Professor Kuninaka, for the presentation. As a reminder to our audience, please type your questions into the Q&A panel on your right, and I will be reading them out to the presenters. The first question we have is from Raj. This is to Kuninaka-san. Were you concerned with micrometeor and orbital debris impact? If you were not concerned, what analysis or design assured you that it was not a problem?
Yeah, so at the moment of the touchdown operation of the Hayabusa 2, so we use the lot of sensor, camera on a LiDAR system, but some of them were contaminated by the fragment of the fragment emanated from the asteroid. And then so the sensing such kind of these sensor has the damaged by the touchdown operation. So that the future mission we need protection mechanisms such kind these sensors at the moment of touchdown operation.
So here's another question. Can you comment on any interesting lessons learned from the first Hayabusa mission? How you address that in Hayabusa 2?
Okay, so in the Hayabusa, for example, we had a lot of the trouble on the way to asteroid Itokawa and the came back operation. One of the serious one is the reaction wheel. So Hayabusa 1 installed the 3 reaction wheels XYZ. But we lost 2 of them, and that is a very serious phenomena. And then, so in order to countermeasure, Hayabusa 2 takes the 4 reaction wheels, XYZZ. It means the so conventional technology. So 4 reaction wheels will be installed the skewed mode, but the Hayabusa 2 takes the XYZZ. So it means the Z directional. So we installed 2 reaction wheels, and then so once we have the Z reaction wheel, we can take the attitude control minimize, and then so we decided to install 4 reaction wheels XYZZ for Hayabusa 2 mission. That is the example of the, our countermeasure.
Okay. What amount of sample may be returned to Earth in the sample return capsule?
Please say it again.
Oh, sorry. What amount of sample is going to be returned to Earth? You expect in the sample return capsule for Hayabusa 2?
Yeah, we have an object to came back 4 days later within the 100 hours after the touchdown retrieval operation. We want to bring transport reentry vehicle from Umera to Japan.
But how much material are you expecting in the capsule?
So minimum object is 0.1 gram, but here we are expecting the amount of the sample.
Excellent. So I have another question. How was the attitude of the impactor and the camera stabilized to make sure that the camera was pointed at the site of the impact?
That is very easy. So a spin operation, spin stabilized. So
okay.
Small camera, D-cam is about only 1 kilogram tiny object, and then so once we release the from the spacecraft, we take the spin maneuver.
Okay. So this is a question from David Buttsworth. We're interested in reentry observation of the Hayabusa 2 capsule. Australian expertise in the area exists, and they were wondering if they might coordinate with JAXA on this.
That is a very important question. So now we have COVID-19. That is one of the problems. We are now investigating how retrieval team enter the Australia government for to protect the COVID-19, and so we are present state we cannot explain the detail of the retrieval operation. That is a very headache problem, present state. I'm sorry, I can't explain.
I can imagine.
Detail.
Yeah. So another question I had. Did the Hayabusa 2 spacecraft observe the site of the impact at close range after the ejecta had already dissipated? And was there any evidence that the material left in the crater was different?
Yeah, so main reason to make artificial crater, scientists request to collect material inside of the asteroid, because the surface of the asteroid take the space weathering by solar radiation, and then asteroid scientists request us to collection of the material from inside asteroid, and then so that the in that sense the new artificial crater shows the inside of the asteroid, and then so that the inside of the asteroid shows the fresh material, and then so that the color is different from the inside and the surface of the asteroid. That is the very good observation for the scientific investigation.
And maybe one more question before we move on to the next speaker. Personally, what did you think was the most challenging or the most exciting parts of the Hayabusa 2 mission?
So whole of the sequence of events and the very exciting one. Today's presentation I cannot show you, but we in the vicinity of the asteroid we released some of the separation robotics. So 3 robotics was developed by JAXA, and 1 developed by DLR and CNES. So that is also very exciting moment. So this exciting operation will be developed by international collaboration. I would like to take the good relationship for the ESA, JAXA, and the space agencies.
Okay, thank you, Professor. Marcus, would you like to introduce our next speaker?
Sure. Thank you, Dr. Kuninaka. That was a great presentation. So moving on to our next presentation for today is going to be given by Jim Corliss on Mars Sample Return in the Earth Entry Vehicle. So Jim is a project engineer in NASA Langley's Atmospheric Flight and Entry Systems branch, where he provides technical leadership and guidance as a project manager, systems engineer, and chief engineer for aerospace and aeronautical projects. Sorry. Jim served as a technology development manager for the Earth Entry Vehicle when it was first conceived for the 2003/2005 Mars Sample Return mission. Afterwards, he was the chief engineer for the Orion Landing System Advanced Development Project, leading to the development and demonstration of an airbag landing system for the Orion Crew Module. And then he moved on to as chief engineer for the Clario Earth Science mission until 2010. He then returned to Orion as the chief engineer and principal investigator of the Water Impact Test Program to verify the performance of the Crew Module for ocean water landings, and then back to Clario again for the Pathfinder mission as the chief engineer until 2018. Jim is currently serving as the Mars Sample Return Earth Entry Vehicle chief engineer. His 26 years of experience at NASA Langley have also included serving as the branch head of the Exploration Engineering branch and as a systems engineer in Langley's aeronautical facilities. Jim came to NASA Langley in 1994 after 9 years at the NASA Ames Research Center, and prior to that, he obtained a Bachelor of Science degree in Mechanical Engineering from the Virginia Polytechnic Institute and State University in 1984. So now, let me now turn it over to Jim to talk more about Mars sample return and the Earth entry vehicle system.
Thank you, Marcus, and thank you everyone for joining us today. So my presentation will begin with a short introduction on the Mars sample return mission itself, and then we'll focus more on the Earth entry vehicle, which is essentially the sample return capsule for the Mars sample return mission. And I'd like to acknowledge that the Earth entry vehicle team actually is quite a large team comprised of 4 different NASA centers. So we're here at the Langley Research Center, and then also the Ames Research Center works with us on the EEV, as well as the Jet Propulsion Laboratory. And I should note that JPL manages the overall Mars sample return campaign. And then the Goddard Space Flight Center is responsible for the capture, contain, and return system where the EEV resides on the Earth return orbiter. And the Earth return orbiter itself is provided by the European Space Agency. So we'll start by discussing the Mars sample return mission itself. And we actually call it a campaign because it is comprised of 3 different elements, 3 different launches. So if we can go to the next slide, please. We'll start with that discussion on the campaign overview. We'll walk through the Earth entry vehicle overview, and then provide a summary of what the current EEV concept looks like as it stands today, and where we're going in the future to finish developing the Earth entry vehicle. So onto the MSR campaign. And as I mentioned, we call it a campaign because it's more than one mission. It's 3 separate missions, 3 launches, beginning with Mars 2020, which launches in July of this year. So Mars 2020 carries the Perseverance rover, which we refer to as the sample caching rover. So its function for Mars sample return, in addition to its primary science mission for Mars 2020, is to collect at least 20 soil and rock samples from around the area which it can access from the landing site. And then we've looked at different strategies for caching those particular samples. The one that you see illustrated in the video that's playing is what we call a depot caching strategy, where the rover goes out to different sites of interest around the landing area, it collects samples, brings them back to a depot where those samples are left for the Mars sample return lander mission, which is the next element of the Mars sample campaign, Mars sample return campaign. And the sample retrieval lander, SRL, as we refer to it, has several components. It has the fetch rover. So that is a smaller rover that goes out and retrieves all of those sample tubes that Mars 2020, that the Perseverance rover left behind for collection. And then it also contains the orbiting sample container, which is a small, not quite spherically shaped container into which the sample tubes are inserted. And that is in the nose of the Mars Ascent vehicle, which you see in the image there. So the fetch rover collects these sample tubes, inserts them into the orbiting sample container located on the MAV, Mars Ascent vehicle. And then the MAV launches from the Mars surface and inserts that orbiting sample container into orbit around Mars for the next mission, for the next launch to come along and retrieve, which is the Earth return orbiter. So this is the spacecraft provided by ESA. And the Earth return orbiter has the capture, contain, and return system that you see illustrated in the lower image there. And that system will rendezvous with the orbiting sample container that the MAV put into orbit at Mars. It will capture that sample container. It will encapsulate the container in 2 layers of containment protection for the purposes of back to planetary protection back here on Earth. So we encapsulate that orbiting sample container, and then we insert it into the Earth entry vehicle, which is, you can see in the lower image, it's oriented upside down there in that particular image. And the sample container encapsulated in these containment vessels gets inserted up into that Earth entry vehicle. The back shell, or what we call the cam lid of that EEV, gets assembled to the vehicle, and then the Earth return orbiter returns to Earth to subsequently release the EEV for an Earth entry here, so we can recover it. So the focus that we'll discuss as we move forward here today is the Earth entry vehicle itself that you see there in the lower image. So moving on to the next slide, we'll walk through the orbital architecture. So this is basically what I just described, but in more of a picture form. So starting with Mars 2020 on the left, that particular launch puts the Perseverance rover down onto the surface of Mars. It collects the sample tubes, and then the ERO orbiter and the sample retrieval lander spacecraft, they both right now are planned to launch in the same year. And the sample retrieval lander puts down the Fetch rover, collects those sample tubes, inserts them into the orbiting sample container on the MAV, which then gets put into orbit, and then the Earth return orbiter, which also launched in the same year, comes and collects that orbiting sample container, brings it back to Earth after encapsulating it in the sample protection containers that I mentioned previously, and then the Earth entry vehicle is released for an Earth entry here, so we can recover the samples. So the next slide starts to show some of the differences between the Mars sample return mission architecture and what Dr. Kuninaka just described for Hayabusa in terms of mission design, and then also you'll see differences with the Earth entry vehicle itself. But in this illustration, as the ERO is approaching Earth, it's initially not on an Earth-targeted trajectory. And up to either 4 to 6 days before we plan the EEV to enter the Earth's atmosphere, the ERO conducts an Earth-targeting maneuver and releases the Earth entry vehicle. And that's one of the first real differences compared to, say, the Hayabusa mission or even previous sample return missions, where our sample return capsule is released 4 to 6 days away from the Earth, whereas you might remember Dr. Kuninaka's video, which showed the spacecraft essentially trailing the sample return capsule into the atmosphere and then burning and breaking up. In this case, we release the EEV very early, and then the ERO conducts a Earth avoidance maneuver to take itself out into space. So it does not re-enter the Earth's atmosphere as previous spacecraft have for sample return missions. So now we have this EEV that's 4 to 6 days from Earth. And in this case, Raj just asked the question in the previous presentation about micrometeoroid concerns. And in this case, we're free flying for 4 to 6 days. And micrometeoroids and orbital debris do become a concern for us. And we'll talk about that in a little bit. So we free fly for 4 to 6 days, eventually reach the top of the atmosphere, and we conduct a ballistic entry into which we haven't selected our landing site now. We're currently notionally considering the Utah Test and Training Range, which is the same range that Stardust and Genesis used. But we conduct a ballistic entry into UTTR if that's the site selected, and then we recover the sample return capsule there. So keep in mind we have this orbital debris issue to deal with, which we'll talk about a little later. And then we have some specific design features that are unique to the EEV that we'll talk about on the next slide. So the EEV itself, we developed here at Langley almost 20 years ago. It was originally developed as an enabling technology for the 2003-2005 Mars sample return mission, which eventually did get canceled. But there are 3 particular unique features about the Earth entry vehicle that are worth noting. The first one that we noted already is that it's passive ballistic entry and descent. And when we say passive, we mean completely passive. There are no electronics, no power, no EDL events throughout the entire entry, descent, and landing. So it's a completely passive entry through the Earth's atmosphere. And then the next unique feature is that we do not use a parachute. And that's part of our strategy for optimizing the vehicle design while also balancing back planetary protection requirements. And part of the rationale for not having a parachute is that when you really work through the probabilistic risk assessment of how much benefit does that parachute provide, it's not a significant improvement in planetary protection reliability over having, not having a parachute. And that's because the parachute system itself is not particularly reliable. We already know that from experience. And the mass that it puts onto the spacecraft it simply isn't worth the benefit that we get from it. And I think, as a lot of people are aware, there's a large gear ratio when it comes with respect to carrying that mass to Mars and back. So, every kilogram is precious when it comes to going to Mars and then having to return that mass from Mars, and it's just not worth it to put the parachute onto the EEV. But because we don't have a parachute, there's a second unique capability that the EEV has, which is an omnidirectional impact energy absorber. So while the vast expanse of a range like the Utah Test and Training Range is comprised of flat, dry lake bed, playa soil, there is always the possibility that we could land on a surface other than soil. And that's a very important consideration for Mars sample return with respect to preserving the science integrity of the samples as well as back planetary protection for the Earth. So in this case, you can see on the image on the left side there that we have this central impact energy absorber, which is a composite cellular structure. So it's composite webs and foam within this energy absorber that crushes on impact if the EEV were to land on some kind of hard surface or a small rock. So that is what we use to protect the sample container, precisely because we don't have a parachute. But I should also note that even if we did have a parachute, we would be required to have an energy absorber like this simply because the parachute system could fail. So those are the unique features of the EEV, and then the current concept that we're working on right now on the next slide is comprised of several different components. So first of all, we're going currently with a 60-degree sphere cone design, and we have some trade studies ongoing right now examining that more closely. But the heat shield material that we've selected is three-dimensional woven heat shield for extreme entry environment technology, or HEAT, which I'm sure a lot of people are familiar with. So that is our four-body thermal protection system, and in this case, we're simply using the insulation layer of HEAT, not the recession layer, which is also available with that particular TPS technology. The backshell TPS is PICA, or phenolic impregnated carbon ablator, and that covers the brown backshell surface that you see in the image. And then the actual structure of the vehicle, and Tim, if you could click one or two times here thank you. The carbon fiber structure of the vehicle is what we call an integrated composite stiffened structure, or ICOS structure. It's a carbon fiber composite foam construction with integral cochured ribs within the structure, and that's what we use as the actual structure to support the forward heat shield and the backshell thermal protection system. And then it surrounds the energy absorber that you see in the center of the image there. And in this particular image, you can see the sample container cross-section with the tubes And in this case, we're designed for a 30-tube sample container. And the EEV, as it's designed now, can accommodate that 30-tube container, as well as the crushable energy absorber that you see here in the image. And if we can click forward a couple of clicks here just to highlight a little bit the composite energy absorber a little more closely, and then a little closer look at the orbiting sample container on the left side here. And it's difficult to make out in that image, but that orbiting sample container, as I mentioned before, is encapsulated in two additional layers of containment that we call the secondary containment vessel and the primary containment vessel. Okay, so next slide. So the outer mold lines of this vehicle are a key aspect of the design because of these requirements that we have, where we're conducting a fully passive ballistic entry with a vehicle that needs to accommodate this Mars sample container as well as a crushable energy absorber. But at the same time, it needs to be aerodynamically stable all the way from entry to the ground. And this is a unique feature or requirement for the EEV because we don't have a parachute. And all previous sample return missions have relied on a parachute for aerodynamic stability through the supersonic and subsonic regimes. And in particular, for our vehicle, the subsonic flight regime is one of the more challenging areas where we are currently concerned about aerodynamic stability, and we'll talk about that in a second. But in addition to that aerodynamic stability, the difficult trade here is that we also want the vehicle to produce as much drag as possible. We're landing without a parachute. We want to try to keep that landing velocity as low as we can. But in general, as you make a vehicle, more draggy, so to speak, increase its drag, it typically becomes less stable. And one of the challenges we have in this particular vehicle design is to balance those two particular requirements so that we produce a vehicle that is stable all of the way to the ground, but also lands at with conditions or velocities that are acceptable with respect to impact loads on the sample. And when we were back in the 2003-2005 mission, you can see the range of different outer mold line shapes that we considered for the EEV back then. And in comparison to the Stardust and the Genesis capsules that you see there on the left, one of the primary features that you'll notice is that hardly any of these EEV shapes have a back shell on them. They're almost all with an open back shell with simply the energy absorber and the sample container as kind of a protruding hemisphere out the back of the vehicle. And that is one of the features to help improve the stability, aerodynamic stability of the vehicle, is to not fly with a back shell, which is often a destabilizing element in a passive entry probe like this. So back for the 2003-2005 mission, we selected that particular 60-degree sphere cone design that you see there. So the challenge with that, and what we've been learning as we've been moving forward, moving to the next slide, is that isn't necessarily the best balance between aerodynamic stability and impact velocity. So what we've been doing is comparing and contrasting the 60-degree sphere cone shape with a 45-degree sphere cone geometry. And a 45-degree shape is what Dr. Kuninaka just described that was used for Hayabusa. So the 45-degree vehicle, we know will be more stable, but of course it has a lower drag coefficient and will produce a higher ballistic coefficient for the vehicle and higher impact velocities. So we've been conducting a number of tests in the vertical spin tunnel here at Langley. The first one in the lower left there is a free flight test. This is what we call a perturbed free flight test of the 60-degree capsule, where we introduce it into the flow stream of the wind tunnel, and we measure its attitude time history throughout the test. And from that data, we can determine what the damping coefficient is, the pitch damping coefficient, and what kind of dynamic stability characteristics it has. And you can kind of get a sense of what that 60-degree performance looks like for that geometry. And then at the same time, we've been testing the 45-degree sphere cone geometry over on the right. A very similar test inserted into the flow stream with an initial angle of attack, and you can see how much more quickly it damps out, how much more quickly the pitch attitude will damp out. And we have found that that is a much more stable design as we would expect. And we're currently in the middle of this trade study right now where we are focused on what are really the differences between these two configurations, not just with respect to stability, but with respect to mass, entry environments, other design considerations, and spacecraft accommodations. But we expect to complete that particular trade study here in the next month and work to make a decision on which direction we're going to go there with that design. So let's go to the next slide. And we'll move on to the other trade study that we're currently conducting, and this gets back to the micrometeoroid concern. So as I mentioned before, we are currently using this ICOS carbon fiber composite construction, which we know is, based on previous studies, is our lowest mass solution for the Earth entry vehicle structure, and we've built the structure before, so we're comfortable with it. We've conducted drop tests with it, as you see in the photograph there. But, and this is a pretty big concern for our mission because of the micrometeoroid risk, during those 4 to 6 days of free flight, we have a high enough probability of a micrometeoroid impact that we need to ensure that this vehicle can still survive re-entry and safely deliver these samples in the event of a micrometeoroid impact. And while that composite structure certainly has some capability, and heat as our 4-body TPS helps improve that capability, heat has a fairly robust capability against micrometeoroid penetration. But at the same time, our current analyses have been showing us that it may not be enough to have heat on a composite structure. So we're currently looking at a titanium aeroshell structure that you see there in the lower left-hand image. And a titanium structure will certainly give us better MMOD robustness, but we do expect there to be a mass penalty that comes along with that. So that we're conducting this trade at the same time we're looking at the outer mold line choices between 60-degree and 45-degree, and we're going to wrap those two trades up together and make a decision on both of those in the next couple of months. Okay, next slide. So to supplement the MMOD analysis, we have several models that need to be validated to really have confidence in our MMOD predictive capability. And what you'll see here is a video showing some of our hypervelocity impact testing of the heat thermal protection system. So on the lower left-hand image here, you'll see one of these particular tests. And micrometeoroids are, of course, very small, but they have a lot of energy associated with them because of the very high velocities. And you can see both in the video and also in the images here. I mean, that lower right-hand image, that MMOD particle went completely through that piece of heat, or I would say at least blew out the backside of that piece of heat. And the upper right-hand image shows a close-up of a crater that did not penetrate completely through the heat material, but does, of course, leave a crater that we need to be able to characterize and to understand the implications of when it comes to the thermal impact to the rest of the vehicle structure. So the way that we get at that particular understanding is to conduct some arc jet tests of the thermal protection system shown on the next slide, where we, in an arc jet at Ames, we will test coupons that are pristine of both heat, our 4-body TPS, and pica, our aft body TPS. So we test those in both pristine and in damaged conditions, and in this case, when we say damage, we mean a crater from a micrometeoroid impact. And then we use these particular ArcJet tests to help us characterize our thermal response models and material models, material response models, and how heat will behave in this kind of damaged state as we go through a heat pulse during reentry. And then from these tests, we can also help validate our thermal response models, which will then feed into the structural analysis or the thermal analysis of the underlying structure of the vehicle. Now let's go to the next slide and we'll discuss some of the drop testing that we're conducting. So this is getting back to the fact that we don't land with a parachute, or I should say we land without a parachute. And we have been conducting some drop tests out at UTTR to validate both our soil models and also the behavior or response of the vehicle to that impact into the soil. So the video in the upper left here is one of our drop tests. We were out at UTTR in November of last year, and we conducted 9 drop tests. This particular test is at 50 meters per second impact velocity. And you can see some of the other impact craters down there below the helicopter. You're viewing the ground from the release hook on the helicopter. And these impacts, the image sequence that you see in the lower part of the slide here gives you an idea of what those impacts look like. And there's a lot of energy involved, but one of the real advantages, at least to the Utah Test and Training Range, is that the soil there, being a dry lake bed, but at the same time, the groundwater at UTTR is very close to the surface. So the soil has a high moisture content year round. And it's a very soft clay type of soil. And you can see how the soil disperses and really moves away when the EEV test article lands. And in these cases, the vehicle fully penetrated into the soil. And you would not see the vehicle if you looked at it after this particular test. It would go down several inches below the surface of the soil. And in the upper right, you see some of the test data from 3 40 meter per second drop tests. And then also there, the black curve that you see there is our Elastine impact model prediction of those 3 impact tests. And this is just an example of how we're using these particular tests to calibrate our Elastine impact models for this unparachuted landing. So let's go to the next slide. And this just shows some of those details for these Elastine simulations. So on the left, you see some of our soil landing simulations. And the thing to note for a soil landing is that all of the impact attenuation is really accomplished by the soil itself, not by the vehicle. So there's very little deformation in the vehicle structure. All of the deformation is in the soil. And in this case, the soil combined with the impact conditions to which we're designing the vehicle will keep the impact accelerations below the 1100 G limit that we currently have established to protect the science integrity of the samples. So that's what a nominal soil landing simulation looks like. And on the right side, you see several videos of what we call off-nominal landings, where now the energy absorber comes into play. So these are landings on a hard surface. And in this case, the energy absorber needs to protect the samples. And for these landings, the focus is on sample containment, not science integrity. And we have currently a 3000 G requirement for these off-nominal landings to protect the samples from losing containment within their sample containment. So that's what the off-nominal landings look like. And there's a lot of material testing and impact testing that is behind those particular simulations and how we validate those models. So just to wrap things up quickly, we're continuing the EEV design and development. Everything's continuing as planned to support the current Mars campaign, Mars sample return campaign schedule. In the near term, as I mentioned, we're going to be continuing these aerodynamic tests of the 45-degree and 60-degree sphere cone shapes. And we'll make that decision between those two geometries here in the next couple of months. And at the same time, we'll make a decision between the titanium structure and the carbon fiber composite structure. And then later in the year, if we can get through the COVID-19 issues, we'll be back out at UTTR conducting some additional drop tests. And then we have our MSAR campaign concept review coming up in August of this year. And then a little further down the road, we'll be building our first manufacturing demonstration unit of the EEV early in FY21. I'll say early in calendar year 2021. So that's all of my material. Thanks for being here. And Jacob, if there are any questions.
Sounds good. Thanks, Jim, for the presentation. We'll now open it up for questions. If you have any, please type them into the Q&A panel on your right. So I have one to get us started, and this is a heat question. So the original Mars sample return mission of 2005 planned to use carbon phenolic instead of heat. And one of the reasons was its flight heritage, and so there was a lot of test data so that we could predict failure probability. Heat is a new material, obviously. So how is the reliability concern being addressed?
Yeah, so that's a great question. And the first thing I should note is that we did consider carbon phenolic in this round of developing the EEV, or Mars sample return, and we found it to be mass prohibitive in this particular mission design. One thing that's very different between the current MSR mission and the 2003-2005 mission is that our sample container is a much higher mass now than it was back then. We're bringing back more sample than we were planning to back in 2003-2005. And along with that comes a heavier Earth entry vehicle, which has precluded our ability to use carbon phenolic for this particular mission. And regarding the reliability of heat, that's a very good point that it has not flown yet, and we have actually put together a technology development program to ensure that heat is ready for mission infusion when we're ready to launch the EEV.
Thanks, Jim. This is a question from Siddharth Krishnamurthy. Was the possibility of the Mars 2020 rover delivering the samples to the retriever lander studied? And if yes, why was a second rover architecture preferred over M2020 bringing the samples to the sample return lander?
Well, that's a great question, and no, I'm not sure I'm qualified to answer that question, actually, simply because my focus is the Earth entry vehicle, and I'm not completely knowledgeable of all of the different architectures that were considered for the sample retrieval lander. So I would love to answer your question, but I don't really want to hazard a guess, because I bet that's a pretty complicated answer, actually. So I'm sorry, I can't answer that question.
That's fine, thank you. This is a question from Eric Geistfeld. Have you studied how TPS damage from a micrometeorite would affect the aerodynamic stability?
So yes and no. That's a really good question. So what we have looked at is when the micrometeoroid impacts the vehicle, there's a momentum transfer. And that momentum transfer will introduce some rates, some attitude rates to the Earth entry vehicle, so that when it does reach atmospheric interface, the vehicle may not be in a purely, nose forward, low angle of attack orientation. So a high enough energy micrometeoroid impact far enough out on the diameter of the Earth entry vehicle could actually cause it to tumble a little bit prior to Earth entry. And we have looked at how the vehicle will behave in that particular scenario and investigated, will it reorient itself during the hypersonic flight regime in that particular case. The other case, which maybe you were actually asking about, the crater that might be in the thermal protection system from the micrometeoroid impact. We have not yet tried to investigate how that crater might influence the aerodynamics of the vehicle and its aerodynamic stability. That's actually an excellent point, though.
Thank you. This is a question from Alex Hoffman. Can you describe in more detail what happens to the samples in an off-nominal landing?
So in an off-nominal landing, when we land on a hard surface, the samples themselves will experience that higher acceleration load that I mentioned, up to about 3,000 Gs. And under those higher loads, that increased acceleration, that not quite a shock load, but that very short duration, high G pulse, will tend to degrade the samples a little bit, in terms of possibly breaking up small rock samples and making the sample itself, the constituency of it change a little bit, because the particles will be reduced in size to some degree. Okay, and the real key, or the real requirement that we have in those off-nominal cases is to protect the samples from losing containment. Okay, within the containers, within the primary containment vessel and the secondary containment vessel. So we recognize we'll lose a little bit of, possibly science value in that particular off-nominal landing scenario. But at the same time, those off-nominal landings are very unlikely based on everything we know now.
Great, thank you. There's a question from Young Ryu. Looks like similarly following up on material composition changes to the Mars samples during impact. I think you already answered that, so thank you. So maybe one more before we move on to the next announcement. This is a question I'd prepared before. Given the concern about sample return containment failing during entry, was the possibility of returning the sample to the space station ever considered instead?
Yes, that's a great question, Jacob, and yes, it was. So there were some studies done, and this was back actually after the 2003-2005 mission was canceled. So in like the 2004 timeframe, we actually conducted some studies that investigated the possibility of bringing the samples back either to the ISS or at least to low Earth orbit, where they could be retrieved by the space shuttle. And then the samples would be inserted into a vault inside the space shuttle to protect them during reentry. And so that particular scenario was studied, but it was determined that it wasn't advantageous over the current mission architecture.
Okay, thank you. So with that, I think, Marcus, do you want to introduce our final speaker for today?
Sure, thank you. And thanks again, Jim, for that great presentation. So for our last talk, I'd like to introduce Dr. Hideyuki Tano. He started working as a researcher at the JAXA Kakuda Research Center in 1992. He is a senior researcher in the high enthalpy shock tunnel HIAST and is currently working on aeroheating of sample reentry capsules such as the HIAST research mission. Dr. Tano received his PhD degree in mechanical engineering from Tohoku University in 2005. So let me turn over to him to fill you in more about IPPW 2021, scheduled to be held next year in Tokyo.
Thank you, Marcus. Okay, so good morning, everybody from Japan. I'm Hidetano from JAXA ISAS. Today I will make an introduction of IPPW 2021 in Tokyo, Japan, hosted by JAXA ISAS. The workshop will be held in September next year, 2024, and following IPPW short course, September 18 to 19. Okay. Yes, the IPPW 2021 will be held at University of Tokyo Hongo campus, which is located in the so really central of Tokyo. And And this is a regional view around the University of Tokyo Hongo campus. And the campus is just 4 kilometers away from the Tokyo Central Station. You can access the Tokyo Central Station from Haneda International Airport or Narita International Airport. From Haneda Airport, it will take about 30 minutes by train. And from Narita Airport, it takes about 60 minutes by Narita Express via train. But if you landed on Narita Airport, we recommend you to take a Narita Express because it's a non-stop direct connect train from Narita Airport to the Tokyo Central Station. And this is a venue of the conference, and that's a Ito Hall. That's a workshop main venue. And the Ito Hall has a large conference room, which capacity is almost 50 persons. And this main hall will be the main conference room for the workshop. And we also keep the the Sanjo Conference Hall for IPPW IPPW short course. Its capacity is a little bit smaller, 120 persons, but we believe it is enough for the short course. And And this is a map of Hongo campus, and you can see there. Oh, that seemed. Anyway, the Sanjo Hall and Ito Hall were marked as red stars. And in Tokyo, we have a good subway system. There are 3 subway stations near around the Hongo campus. You can see there purple circles. These 3 circles indicate subway station. And it takes almost 15 minutes walk from Hongo campus, Hongo Sanchome subway station to the Ito Hall. And during the workshop, lunch will be a free time, and you can take lunch on campus cafeteria or restaurant. Since they are for the student, and we believe they are quite reasonable prices. And alternatively, since the Hongo campus located in the center of Tokyo, you can find so many good restaurants and cafeterias and everything around near to the campus. Of course, the price is a little bit expensive. And so the next one is accommodation. We have many hotels located near to the Ueno Station and Suidobashi Station. Both stations is almost approximately 1 kilometer distance from the venue, the University of Tokyo Hongo campus. And the price, the price of these hotels are almost 10,000 Japanese yen to 20,000 Japanese yen a night. And the local organizing committee will work with travel agencies to set up the recommended hotel list and so online reservation system. It will be come soon. And this page shows their schedule of workshop overview, and including a short course. And the short course will be from September 18 to 19, and so workshop will be followed by the main workshop from September 20 to 24. And we also planning some social tours but unfortunately it's under planning. And since we have so many sightseeing places in Tokyo, we believe we can provide a good social tour. The IPPW banquet is also under consideration. And we are planning two technical tours. The first one is a tour to JAXA IDAS Sagamihara, Sunday afternoon after short course, and that will be a half-day bus tour. And the other one is a tour to JAXA Tsukuba. That will be also half-day bus tour Friday afternoon in the workshop. And that's so the almost tentative local organizing committee list of the local organizing committee for IPPW Japan. And the chair of LOC is Professor Kuninaka Sensei. He was already introduced, but he's a director of general in IDAS. And now there are 5 local organizing committee staff. Professor Suzuki and Professor Yamada and Professor Dr. Akita and Dr. Marcus from NADA and me. Yes, that's all my talk for the introduction of IPPW 2021 Tokyo, Japan. Thank you for your attention, and we are very looking forward to seeing you in Tokyo next year. Thank you so much.
Thank you, Dr.
Yes, that's all right. Yeah.
Oh, thank you
that's
for
all. Thanks.
that exciting preview of IPPW 2021. I would like to take a brief moment to remind our audience of our full-length article opportunity. We have organized a new AIAA Journal of Spacecraft and Rockets virtual collection for this year, titled Innovative Methods, Instruments, and Materials for Planetary Entry. And we're specifically looking for journal quality full-length articles based off of your IPPW 2020 material. Articles will go through the standard JSR peer review. I would like to thank Carl Edquist of NASA Langley for agreeing to be the associate editor in charge of this collection. Carl has been an integral part of IPPW and the IOC for many years now. Due date is September 11th, 2020, and the submission site is already live on JSR Manuscript Central. More details can also be found on our IPPW webinar website. And with that, I'll hand it off to Jim Cutts for closing remarks.
Thank you, Jacob. I'd like to end today's session by thanking Ashley Corzin for her support for the IPPW webinar series, and to Marcus for organizing this particular session and working with our Japanese colleagues to make it happen. I'd like to thank our 3 presenters, Dr. Kuninaka, Dr. Tano, and to Jim Collis for their stimulating presentations. And of course, we all look forward to seeing Toshi and Hideyuki in person in Tokyo next year. Finally, I'd like to thank Jacob for his expert management of the Q&A process, and to Tim Bryce and the rest of the digital team that has made this run smoothly. Our next and final webinar of the series will be in 2 weeks' time, but it'll be back at the usual time of 8 a.m. Pacific. The topic is new concepts in lunar and planetary exploration, and the focus will be on landed missions to the Moon, Mercury, and Venus. We look forward to seeing you all back then for a rousing finale. Thank you, and good day wherever you are.